Okay. So it's a great pleasure to welcome Fabio Picucci today. He's both a Clay and a Black Hole Initiative Fellow at Harvard Center for Astrophysics. He got his PhD from the Scuola Normale Superiore in Pisa. And he's an expert on the theory of observations of high-Z black holes, and he's also very involved with JWST, which is many programs there, which is great. And he's also involved in planning next-generation observatories, such as NASA's AXIS in the X-ray, and HWO in the UV, optical, and infrared. So today he's going to be talking about little red dots.
Yes.
Thank you. Thank you.
Mainly about it. All right, so hi everyone. Thank you for hosting me. It's a great pleasure to be at NYU. I've never been here before, actually. So today we will go on a journey to explore the famous, or now infamous, little red dots. And in a few slides, I hope that you will see why I call them the masters of disguise in the High-Redshift universe. But let's start from a little brief cosmic history of black holes, just to set the timeline of the story. Now we're about 13.7 billion years after the Big Bang, and the peak of quasar activity, or black hole activity, happened about 10 billion years ago. Now, the first supermassive black holes were already in place far less than 1 billion years after the Big Bang, while the black hole seeds, so the first population of black holes, were formed around redshift 20 to 30, so a few hundred million years after the Big Bang. Now, most of my talk...
When you speak of those seeds, what masses do you think they have?
Seeds. So,
they're seeds. When you call it a seed, is it an apple seed, or is it
black hole
the
seeds,
solar mass thing?
Yes, black hole seeds typically are categorized in light seeds. Say, imagine 100 solar masses, or heavy seeds, 10 to the 4 to 10 to the 6
So when
solar
you say
masses.
they form at 20 or 30, are you thinking of light seeds or heavy seeds?
No, redshift 20 to 30, both of them. We know that light seeds formed for sure, because we know that the first population of stars formed and they were very massive, so they are most likely to have formed light seeds. The big question is, do black hole seeds happen?
Right, but you're saying that the answer is yes, that they're there at 20 to 30.
Yes, light seeding happened
But
around.
I'm asking about the heavy seeds.
Yes, exactly.
You're saying they're also there.
Well, it's
that's
possible. It's possible that heavy seeding happened during the same cosmic period. Yes, we don't know for sure. We haven't found them yet.
There's a
for
lot
sure.
of controversy.
Yes,
whether
there's a
it's
lot of
possible.
controversy, and also forming heavy seeds is much more unlikely.
Okay, sorry, you just
than...
asserted it as if we
Yes,
should know
yeah,
it,
of
that
course.
it's true.
Yeah. Feel free to interrupt me whenever you want. So most of my talk today will focus actually on the little red dots, so typically in the redshift range between 4 and 10. However, in the last part of my talk, I will actually describe how this population of possibly AGN in the High-Redshift universe are fundamental to understand other populations of black holes, especially at higher redshift, so the black hole seeds that we've been talking about a few moments ago, and also local populations of black holes. So, in other words, the little red dots, if they are really AGN, they may be bridges connecting different populations of black holes. But let's talk about AGN, broadline AGN discovered by JWST, so the so-called little red dots. If you haven't heard about them, the little red dots are tiny, compact, kind of cute galaxies that are typically discovered around redshift 4 to 8 by JWST. They are popping out everywhere in JWST fields, and typically they are 10 to 100 times more numerous than the faint end of the AGN luminosity function around redshift 5, so in the same redshift range that these objects are discovered. Now, what are they? This is the big questions, and the reality is that nobody knows yet. We know for sure that they are compact. Some of them are 100 parsec in radius, some of them are even smaller than that. And typical interpretations of the physical nature of the little red dots is divided into two broad classes. So either they are AGN dominated, so most of the light comes from a supermassive black hole at the center, or they are star formation dominated, so most of the light comes from stars, actually huge amount of stars. Now, in the AGN-dominated cases, typical bolometric luminosity, so total luminosities of the supermassive black hole, would range between 10 to the 45 and 10 to the 47, so they are not as bright as quasars. Quasars are like 10 to the 47, 10 to the 48 terc per second. About 60% of them show clear sign of broad line regions, so they do seem to host an AGN. But if all the little red dots contain a supermassive black hole, this would imply that constant accretion density, so say solar masses per year per cubic parsec, between redshift 2 and 9, which would be quite problematic for theories of black hole formation and evolution. On the other side, if they are star formation dominated, you see stellar mass ranges between 10 to the 8.5 and 10 to the 11. So some of these objects may be as massive as the Milky Way, but they are 20 to 50 times smaller in radius. So there are several papers out there trying to understand the physical properties of these galaxies, and some of them are listed here. However, both interpretations have warnings attached. In particular, in the AGN-dominated case, black holes seem to be overmassive, very overmassive with respect to the stellar content of the galaxies. And also black holes are completely undetected in the X-rays. In the other case, if they are mostly star formation dominated, the implied stellar densities are huge because these objects are very compact and some of them are very massive. So for the remaining of my talk, I will be describing these three issues one after the other. Let's talk about the, please, yes.
Can you say how you know the redshift of these?
How do we know the redshift? So there are about 500 photometrically selected regular dots, and in this case the redshift is photometric. There are some uncertainties, but most of them are quite accurate. I would say redshift uncertainties in those cases about 0.2, something like that. Spectroscopic determination of redshift is very, very accurate, and we have about 20 spectroscopically detected little red dots so far. So the spectroscopically detected are sure. Photometrically detected, I mean, they could be like lower redshift solutions, but they are really unlikely to happen.
For photometric redshift, don't you need to know some theoretical assumption about what the object is to?
You have assumptions on the general structures of the SCD, which would be like either galaxy or AGN, but both models actually give pretty consistent redshift with each other. Because the SCD shape, especially at lower, smaller wavelengths, so below 3.5 micron, it's pretty similar to each other. So there are not really much uncertainties in the photometric determination, actually. Yes?
How do you know that they're 100 parsecs or even smaller?
Oh, you just you take one filter, for example, F444, which is one of the longest wavelengths, and you just measure the size, the appearing field. So some of them are actually resolved, most of them are unresolved, meaning that they are even smaller than that. To measure accurately the radius, when you actually resolve them, you need to know very well the PSF of the instrument, but by knowing the PSF of JWST, you can actually make very good estimates. And there is actually a little red dot that is gravitationally lensed, so you can see the structure very like larger because it's lensed, and we can see resolve the radius at 32 parsec. So this thing is actually 32 parsec of effective radius. It's really crazy how small they are, these things.
So how many pixels they are?
How many what?
Like how many pixels like the pixels of these?
Pixels.
Like because this is very small, right? So how many pixels that should be enough to resolve?
I would say about 7 to 10. I would say, yeah, in near camp at least.
They are very isolated. They are not.
Yeah, no, there is not a large. They are basically yeah, there is no clustering studies of little red dots so far, so they are pretty much isolated, yes. See, yeah, I would say I was thinking it's about 7 to 8 pixels, 7 to 10 pixels would be like a typical size.
It could, this is, I assume, 4 pi volumetric luminosity, assuming
Yes.
it's isotropic. So it could actually be very much smaller if we're just picking up the ones that are aimed at us.
Yes,
Is there
so
any evidence against that? Like that would sort of imply a spectrum of brightnesses.
yes, so this is an excellent point. Actually, one of the proposals to explain why they are X-ray undetected, as I was saying, and I will get to that later, is that they are actually highly beamed. So the total volumetric luminosity is much lower, but you are seeing them close to the beam, so close to the jet, so you are thinking that they are much brighter than they are. Yes, that's a possibility. But on the other side, the negative aspect of this interpretation is that if they are really highly beamed, then it means that there are many more than what we are seeing, and we are seeing already too many, like by 2 orders of magnitude, if they are black holes.
Right, although they would then be much, much less massive, and so
They
maybe,
would be less
maybe we
massive,
don't
yes.
have a strong opinion of how many we should see.
Yeah, I mean, they could balance out.
I
Yeah.
was wondering, it seems like you would, if there's a big enough population, you would actually see from the, if you assume they were all the same but had some beaming angle,
Mhm.
you would arrive at a prediction for what the spectrum of luminosity should be. If I said that coherently, you probably do.
So, I will be talking about the beaming issue when I
Okay,
get
I'll wait,
to
I'll
the
wait, yeah.
X-rays, because it's very important for that. So maybe I will answer your question at that point. So let's get to the overmassive black hole problem. That was the first one pointed out about 1 year ago. And in general, we've known for a long time that the mass of the central black hole correlates with some properties of the host. And for example, one such relation is the MM star that says that the central mass of the black hole is about 1,000 or 0.1% of the stellar mass of the host. But this is not always the case, and JWST observation in the last couple of years have shown clearly and consistently black holes that seem to be very overmassive with respect to the stellar mass of the host. See this panel in particular, in which JWST detections are here in yellow, while this is the local relation. So these black holes do not seem to be 0.1% of the stellar mass, but rather 1%, 10%, or even a record holder 40% so far. From a theoretical perspective, it's even more interesting that other relations, like the relation between black hole mass and velocity dispersion, and the relation between black hole mass and dynamical mass, seem to be still valid. So it's only the black hole to stellar mass relation that seems to be completely off. So from another more artistic
Sorry, why do you say it's valid? It still seems like the points are still higher than the lines.
I mean, they're much closer to the local relation. Maybe these ones here are a little bit higher, but they're much closer than the other ones. And also the dynamical mass seem to be quite convincing at higher redshift. So it just means that the mass of the galaxy is there, what is traced by dynamical mass. It's just not forming stars fast enough. From another artistic perspective, as you can see in this illustration done at the CFA, the same supermassive black hole is contained in a much smaller galaxy in the High-Redshift universe. I also wanted to point out that typically we don't think about it, but JWST is allowing us almost to reach intermediate mass black hole range at very high redshift. So we are really there to be detecting 10 to the 5, 10 to the 6 solar masses at redshift 5 or 6. So this is something very remarkable. This is not the first time that JWST that overmassive black holes were predicted or noticed. About 20 years ago, there were already some papers that were suggesting that the ratio between black hole mass and stellar mass should increase with redshift. And there were also some sporadic observations pre-JWST. But now, with JWST, we have an explosion of detections of black holes that seem to be very overmassive. Now, there are two most important questions here. So first of all, is this an observational bias? So are we observing overmassive black holes just because they are more massive, so brighter, so intrinsically easier to detect? And also, are the stellar masses and black hole masses accurately estimated? And this is a very important point that actually we are not really still sure about that. But why are we noticing this now in the High-Redshift universe? Why JWST is so revolutionary in this? So give me like 10 seconds of Italianity just to say that more than 700 years ago, Dante and Virgil came out of the Inferno in, yes.
How are the black hole masses measured of these objects?
Broad lines. Typically between redshift 4 and 7 you can measure the H alpha. So by how broad the line is, you have correlations that are studied mostly in the local universe, and assuming that they are still valid in the Redshift universe, you can get the black hole mass. So basically from how broad the line is and how luminous it is.
So to bounce back on this, how can you assume that some correlations are valid in the local universe, but then point out that some others may not hold?
Yes, it's possible that the geometric factor, the shape factors are different, especially if the accretion mode is completely different. For example, if you are determining these correlations from like lower Eddington ratios, so below Eddington, and they turn out to be super-Eddington, it's possible that the geometric factor of the accretion disk may be different. But even though there are studies now that show that the geometric factor shouldn't account for errors of more than a factor of 4 to 7. So these things are overmassive by a factor of 70. So attributing all the effect to geometric factors in the determination, it's very unlikely in my opinion. Yeah. So I was saying, the little Italian part, that Dante and Virgil came out of Inferno 700 years ago and said that they could see once more the stars. And this is to some extent what is happening with JWST right now, because this telescope is observing smaller supermassive black holes in the High-Redshift universe. They are not outshining the host galaxy, so we can see and measure the properties of the stars once again. So this paper came out about 14 months ago, right now, and this was the first one to point out that black holes are apparently very overmassive in JWST fields. In particular, we executed a very accurate statistical analysis of the correlation between black hole mass and stellar mass. We corrected for observational biases and also predicted JWST observability of especially lower redshift, lower mass black holes. In this study, we used the 21 galaxies that were available at the time. You can see them here in the black hole mass versus stellar mass plane. They're all spectroscopically confirmed by NIRSPEC between redshift 4 and 7. The black hole mass is estimated via the H alpha, as I was saying, and the stellar mass is available. You can see the local relation here with the scatter, and these 4 horizontal lines are the minimum black hole mass necessary to execute at least a 3 sigma detection of the H alpha at the 4 different redshifts of interest that you see here. We used an MCMC methodology to infer the redshift relation. In particular, this is based on 3 different ingredients. We started as a prior from the local relation. We included stellar mass functions between redshift 4 and 7 to assign different weights to different galaxies, and also the JWST H alpha limit that I mentioned before. So all of this goes into the likelihood function that we actually took from a paper by David in 2010. And we also included a correction term for a flux-limited survey bias, meaning that we are correcting for the fact that observing overmassive black holes is intrinsically easier. So all of this goes into the inference of the High-Redshift relation, which we find to be the following, shown in red. So in practice, we find a high-redshift relation that is 10 to 100 times overmassive with respect to the local relation. And the standard intrinsic scatter of this relation is about 0.7 dex, which is larger than in the case of the local relation. And also with a t-test for every stellar mass, in, for example, this one, we concluded that the 2 relations are statistically incompatible with each other at more than 3 sigma. So people ask me sometimes why the data seem to have a much shallower slope than actually the high-redshift relation that we find. This is because the algorithm is taking into account that we are probably missing data here because the black hole masses are too low to be detected. So it's automatically correcting the slope, obtaining a slope that is similar to, but actually not exactly the same as the one of the local relation. We also carefully explore the effect of the flux limit on how the bias correction term affects our results. So basically the finite sensitivity, and here the JWST mass limit at redshift 5 is indicated, is about 10 to the 6.2, is basically skewing the observables towards a larger mass. So observing overmassive black holes is intrinsically easier. But because JWST limit in H alpha at the redshift 5 is actually much deeper than most of the observations, the bias shifts the intrinsic rate inferred relation down by 0.2 dex, which is basically very small compared to the scatter of the relation. Now, after this paper, that paper came out, many other JWST observations were consistently showing the detection of very overmassive black holes. So we made an updated plot, and you can see that the high-redshift relation also is well describes also the additional data, especially at larger black hole masses. Now, what do we do once we have the high-redshift relation? We can make predictions, and JWST strength resides not only in detecting very distant black holes, but also very small, so lower mass objects. In particular, in these plots, we show the expected surface density of black holes with a mass lighter than the smallest black hole detected so far, so about 10 to the 6.5 for the local relation and the high-redshift relation. So the inferred high-redshift relation predicts that the distribution of smaller supermassive black holes peaks at a host stellar mass at about 7.5 to 8 in log, while this is much lower than what the local relation predicts, and it's generally consistent with data from JWST are showing. Also, our high-redshift relation yields a higher value of detectable black holes with a small mass, and we predict that boosting factors of about a factor 5 at redshift 4 and a factor 18 at redshift 6. So basically, a search of low mass black holes in existing JWST surveys will provide a very robust test of the MM-star relation that we found. We also investigated the general mass distribution, so not only small mass black holes. And in particular, this figure is displaying the expected surface density of black holes with a mass lower than what is shown on the x-axis, assuming the high-redshift relation. So we expect many more black holes out there in existing JWST fields of the ones that have been found so far, and we have yet to detect these sources for several reasons. Maybe they are just inactive with duty cycles of 1 to 10%, or the host, so the galaxy, is outshining the central AGN, so you cannot see the central black hole, or the AGN is obscured, so it's not easily recognizable by standard line diagnostic, as I was mentioning before.
Sorry, and
Yes.
that just was too intense for me to go. The points that are on there are the low redshift, like in the previous slides?
The previous one.
The previous slides had, well, maybe a few ones back, had a color code like 4, 5, and 6 were red, orange, yellow, and for the galaxies. In fact, sorry, it was in between. But anyway, you had a color scheme.
Oh, this one?
Next one, sorry. There, the color scheme was equals
Yes.
4, 5, and 6. Is that the same colors? What was the data that was in red, yellow, and blue on the one where I stopped you?
Oh,
You must have said.
oh, so
that
this is, so you're talking about this?
No, this one, right. So I just didn't assimilate what those data points were.
Yes, this is still, sorry, I should have put, this is exactly the same color scheme as before. So redshift
Okay.
4, redshift 5, and redshift 6,
And
yes.
then what JWST is saying is that it's a at the higher, what's the black line again?
So the black line is the surface density from the CHEER survey. So basically in this particular case, they found 8 sources in 72 arc minutes, okay?
But that's
this
over
is
all different redshifts, or?
This is a median redshift of 5, so it would be compatible approximately with these lines, yes. So what this plot is saying is that in the fields that we already observed, there are actually many more black holes than the ones that we already found. And we are missing quite a lot of them for the reasons that I mentioned before. So maybe they are inactive, maybe they are in galaxies and the host is outshining the AGN, or maybe we cannot see line emission because they are completely obscured. And so if the overmassive thing is correct, this comes directly from it. So this is a straight prediction from the High-Redshift relation that I mentioned before. Yeah, we can also chat later. I'm happy to answer any questions. I just wanted to go here.
So this is all predictions after you do the MCMC, right?
Yes. Yes, correct. So we start from the data, we do the MCMC, we get the High-Redshift relation, and these predictions that I just mentioned come directly from the High-Redshift relation. So if the High-Redshift relation is correct, these ones are correct.
So just maybe to tease David Hawk, how would you know if the likelihood is the correct one to use?
So you're teasing him or me through him?
Yeah, no, I'm just asking you, like, how would you?
I don't have to answer that question.
I admit we haven't tried any other. I use that paper because I like that paper. I actually learned a lot from that paper, so I don't know. I can't answer this
It's
question.
a simple choice, but it is true that when you do these 2D problems, there are choices.
Yeah.
So
Yeah, we should chat about that, actually.
Yeah.
I think you...
I doubt it matters though, because you don't have a huge amount of data.
So what was this LRD?
Hmm?
What's the LRD?
Where? Here in this plot?
Yeah.
Oh, I haven't talked about this plot. I'm going there, yes. LRD is little red dot.
A little bit.
Yes, so it's just the acronym. So I wanted to get to this slide, and we're basically done with the overmassive thing. I will skip a few slides because I want to get to the other parts, and I'm actually happy about answering questions. So after our paper came out, there was this very interesting paper by Nayoshi and Ichikawa in which they provided a physical interpretation of why black holes could be overmassive. And in particular, they say if we want to align the cumulative mass density that comes from assuming that all the little red dots contain a supermassive black hole to the observed mass density, a redshift 4, we basically we need a very high radiative efficiency. So it needs to be double than the standard one of 10%. So they assume that black holes are basically rapidly spinning. And also they place an upper bound on the stellar mass of the galaxies not to break lambda CDN. And this gives a lower bound for the black hole to stellar mass relation, that is this one that is blinking right now. And this relation that they find completely theoretically is virtually indistinguishable from ours, that we find empirically from JWST. And also with a graduate student from Dartmouth and also Ryan Ecox, we explored the effect of the AGN fraction. So the AGN fraction is the fraction of light that comes from an AGN versus stars at a specific wavelength, in this case at 0.5 micron breastplate. So by doing STD fitting, we find that for 13 little red dots for which we have both NIRCam and MIRI data, we find that the best fitting AGN are very high. They typically range between 40 and 85%. And assuming that they are accreting at the Eddington rate, we find that the black hole masses are consistently 2 and even 3 orders of magnitude higher than the local relation. Just to conclude the part of the overmassive black holes, I just want to shut up a little bit and make you pause on my voice, and I want to show a little animation that they prepared at the CFA for a press release that we made 1 year ago, and I think it's pretty nice and cute. Alright, so to conclude the description of the overmassive black hole, I wanted to note that the high-redshift black holes that we are detecting right now with JWST, they are not really massive in absolute terms. So this is a pictorial representation of the current black hole horizon. So this plot is basically telling you for each black hole mass what is the farthest redshift that you can observe a black hole, assuming that it's accreting at Eddington. The 21 blue points are the 21 overmassive black holes that we used in the paper to derive the overmassive relation. And as you can see, they can be formed from light seeds, so again, as I was saying, approximately 100 solar masses, up to 1000 solar masses, from Eddington limited accretion on light seeds. So JWST is really allowing us to reach farther in redshift, but also lower in mass than ever before. So this concludes the part of the overmassive, and now I will be describing one of the most important and interesting topics that we're talking about in the high redshift community. So the so-called X-ray weakness problem. To present it very briefly, most little red dots are undetected in the X-rays, not even as singular objects, but also in the stacking analysis, leading to the so-called X-ray weakness problem. So, for the first time, we proposed a solution to this problem using GRRMHD simulations, so general relativistic radiation magnetohydrodynamic simulations, of super-Eddington accretion onto a 10 to the 7 solar mass black hole at redshift 6, which represents the median population that we think we are observing. So the punchline is that the SCD, so the spectral energy distributions that we find, are extremely intrinsically X-ray weak. So the SCDs are generating very, very low X-ray photons compared to the local counterparts. In particular, the highest levels of X-ray weakness occur in black holes that are accreting just mildly super-Eddington, so just above the Eddington rate, with zero spin, and also due to large inclination angles from the jet. So the X-ray bolometric corrections that we find in these simulations are extremely large. In general, X-ray bolometric correction is the ratio between bolometric luminosity and the luminosity at 2 to 10 keV. So the higher this number is, the more X-ray weak the source is. In particular, in this plot, in the rest frame, shows the bolometric correction as a function of the log of the Eddington ratio here, spin values as different symbols, and also inclination angles, so different colors. Now, without going into too many details of this plot, you can see that corrections above 100 are easily achieved for black holes accreting just above Eddington. Consider that for standard SCD, bolometric corrections are typically here, so 20 to 30. So 100, it means that it's emitting very few X-rays. Now, if the source is not at redshift 0, so in the rest frame, but is shifted at redshift 6, then the SCDs are so steep that the X-ray emission is completely shifted out of Chandra band. So you basically see nothing in the X-rays, and in fact you see that bolometric corrections in excess of 10 to the 4, so extremely X-ray weak, can be achieved. So how do the SCDs look like? So here I show our reference X-ray weak on the left and X-ray strong on the right SCDs. The red SCDs in any panel show the average, the SCD average over the solid angle, while the gray lines show the STDs as viewed from inclination angles from 10 degrees, so very close to the jet, to 80 degrees, so very far from the jet. Now, STD strong in the X-rays have a much harder spectra with a very high energy bump, as you can see here, while these features are completely invisible, so they are not present in the X-ray weak scenario. So X-ray weak STDs are very soft and steep in the X-rays. Now, when these are redshifted at redshift 6, the X-ray weak spectra are completely invisible to Chandra, except if seen very, very close to the jet, as blazars, you would say. Instead, next generation observatories, such as AXIS, for example, will be able to observe these sources that are X-ray weak from any angle. And this talk is, I'm very happy that I will be able to add this little intermission. This is the first time that I talk about this, because if you heard, AXIS was selected for Phase A by NASA on Thursday. And I am actually in the science team of AXIS, so I'm very happy about this selection. And I actually worked quite a lot on the first pillar of AXIS science, which is actually High-Redshift studies and discovering the seeds of the first supermassive black hole. So I am particularly happy to give this talk today and be able to talk about the AXIS selection. So how steep, going back to the SCDs, are our spectral energy distribution? In this histogram, I show the photon index of all our spectra. Photon index indicates how steep the spectrum is. Typical values in local AGN are 1.7, 1.8. And as you can see, the majority of our super-Eddington STDs have a gamma larger than 2, and the most common value is actually an extremely steep 4.4. Now, as I was saying before, answering your question, the effect of the viewing angle or beaming is very important in these STDs. In particular, in this plot, you can see that the same supermassive black hole accreting at exactly the same accretion rate has peak fluxes that differ by a factor 30 if you change the inclination angle between 10 degrees, so very close to the jet, to 80 degrees, so very far from the jet. So in general, observers that are aligned with the jet will see very hot emission from the accretion flow. Other ones will be mostly seeing optical to UV emission. There was a question.
I was wondering, the X-rays are coming from the accretion, not jet, or both?
If you wait 2 slides, I'm getting.
Okay.
Yes. And also I wanted to show this plot in which I showed the alpha X. The alpha X is basically saying what's the ratio between optical UV emission to X-ray emission. And our SCDs are shown as points here. And this is the relation typically found in standard AGN. And as you can see, many of our super-Eddington SCDs are characterized by values of the alpha X that indicate an extreme X-ray weakness of these sources. As promised, going to your question.
Was that scattered from different viewing angles, or was that?
This is the entire collection of SCDs, so yeah, you are changing also the inclination angle here, yes. And as promised, these are plots colloidal in the colloidal plane of the accretion onto the supermassive black hole, which is always at 0, 0 coordinates in the 4 plots. And you can see that the inner structure of the accretion flow actually shows the physical difference between X-ray weak on the left and X-ray strong on the right SCDs. In particular, enhanced X-ray emission comes mostly from the base of the jet and the walls of the funnel when you reach much higher temperatures, 10 to the 8, 10 to the 9 Kelvin. And also jets that produce very strong X-ray emission are also much more relativistic, as you can see in the beta gamma. So typically, enhanced X-ray emission comes from much higher temperatures and also more relativistic jet. So how does all this apply to the case of the little red dots? In this plot, I show as a function of the bolometric luminosity here, the observed bolometric correction, 2 to 10 kb, The yellow points here are the lower limit on the bolometric correction in JWST fields, Maiolino and Yue, and also the red star indicates the stacking, the limit on the stacking analysis. And this is another type 1 AGN that was discovered by JWST and is so far the most X-ray weak AGN ever found. And here I show our SCDs, and in particular the observed 2 to 10 kV bolometric corrections as blue points. These are the entire collection of SCDs, also from different viewing angles. And as you can see, the SCDs can explain not only the single points, but also the stacking limit. Okay, now third, and yes.
So for these X-ray weak signals, you said you have to assume it's slightly super-Eddington, is that right?
Yes, all these simulations are slightly super-Eddington, yes.
And so like, is
I
that?
mean, we go up to 30 super-Eddington, but the most X-ray weak are actually up to 4, yes.
So, like, I mean, in those simulations, is that put in by hand, or how exactly is that accomplished?
The accretion
The
rate.
super-Eddington accretion.
Oh, so basically you run the simulation, you wait until you reach a stable condition, typically 10 to the 3, 10 to the 4 gravitational times, and then you see what is the accretion rate that you are reaching at that point. And that's the accretion rate that we take as a median, an average for that simulation. So of course, during the simulation, you have varying accretion rate, but we take the snapshot at the point where we are taking. Yes, so I actually want to talk a little bit about the stellar density problem. This is still work in progress. The paper is not out yet, so I'm very curious to hear what your opinion is about that. So this problem comes from the issue that I mentioned at the beginning. The little red dots are very compact, so this is not in doubt. We know that they are pretty compact, and some of them have stellar masses that are comparable to the Milky Way. So you can imagine that this would lead to an extreme stellar density. So just how dense are some of these galaxies? For the most extreme, you can imagine to take the entire Milky Way galaxy and squeeze it into a galaxy that is 1/50th in radius, 1/50 in radius, so extremely compact. In particular, in this latest paper by Bug, and they are studying 3 spectroscopically confirmed little red dots between redshift 7 and 8, you can see that the effective radius is typically lower than 100 parsec, and this would lead to effective surface densities that are higher than the highest core density ever found in globular clusters. So these things are very large. But with an undergraduate student at the CFA, we actually did a systematic study of all the 500 approximately little red dots, mostly from Cosmos Web and Primer. And assuming a Plummer density profile, we calculated what is the core density at 1 parsec radius, core density in terms of solar masses per cubic parsec. And this is the probability density distribution that we obtain. This line indicates the maximum core density ever found in globular clusters by Phil Hopkins. I think I was here like 1 or 2 weeks ago. And we find that 35% of all the little red dots have a core density that is higher, up to 4 orders of magnitude higher than the highest core density ever found in globular clusters. And some of them, especially those in the 7 or 8 or even 9, these densities are higher than the density required for a runaway stellar collision. So it's very likely that weird stuff is happening right there. So just to give you a realistic idea of how dense these things are, this is also the density of the solar neighborhood, so a very sparse environment, right? So there is the same difference between the stellar density in the solar neighborhood and the highest stellar density in the little red dots, as there is a difference between being alone in this room, room 940, and having the entire population of China in this room. So this is how dense some of these things are. So the question is, does the stellar core collapse? And you may imagine that I am a black hole guy, so I want black holes to be there. So my point, as you can imagine, is even if you don't want black holes there, you're gonna form a black hole there. So we investigated this question. We are actually, the paper is not out yet, with 3 approaches. In particular, a Fokker-Planck evolution of the stellar density profile, n-body simulations, and analytical calculations of the mass of the very massive star that could form at the center. Now, regarding Fokker-Planck approach, we started with an initial state, so a simple Plummer density profile, and we evolved the system for relaxation time of about 500 megayears. The core collapse time is about 760 megayears. So after a core collapse time, you find that the final state, the core density is 4 orders of magnitude higher than the initial state. We use these conditions to run n-body simulations, which are still running, but I can tell you that the densest n-body simulation that we are running so far, with a density of 10 to the 8 solar masses per cubic parsec, you have the formation of a very massive star of about 3,000, so I need to update this, we reached about 3,000 solar masses in the very massive star. Also, to conclude, with analytical approach, we are trying to understand what is the mass change for a very massive star that could form at the center, and we are calculating it as the addition between mass added via stellar collisions and mass subtracted via stellar winds, because once you form a very massive star, this is also ejecting a lot of mass around. So, using standard prescriptions, we say that the mass of the very massive star that is added is about 3% of the star formation rate, while you can use your favorite prescription for the stellar wind mass loss. And with this approach, in a very short time scale, a few hundred of mega years, so this is the dynamical time, you get the formation of a very massive star that reaches an equilibrium mass of about 10 to the 5 solar masses. So does the stellar core collapse? It seems so, and so far we find a range of very massive stars, masses that are between 10 to the 3 and 10 to the 5 solar masses. Alright, now in the last 5 minutes, I promised at the beginning that I was going to talk also a little bit about other populations of black holes. So I just want to give my opinion why the little red dots are so interesting right now, and there are so many papers every night on arXiv. They are very peculiar, never before seen, they are cute to some extent, but assuming that the black hole or the aging interpretation is actually correct, the little red dots may be black holes at intermediate mass and intermediate redshift, so they kind of erect bridges between higher redshift and lower redshift populations of black holes. So let me ask a couple of example questions that could show the importance of black holes in the little red dots. Regarding the high redshift range, do they contain information on their seeding mechanism? And regarding the lower mass range, what do they morph into in the local universe? Because we don't see local little red dots. So if you think about this configuration with these 2 bridges, and this is my second Italian moment of the talk and the last, this reminds me a little bit of a beautiful place in my beloved city of Rome. I spent 5 years there, I studied there. So this is the Tiber Island. It is a beautiful boat-shaped, very small island at the center of the Tiber River in Rome. And you can see that it's connected with 2 bridges to the 2 shores of Rome. And if you are passionate about Roman history, like I am, you will also know that the Tiber Island was fundamental to understand the entire settlement of Rome, so how the first peoples arrived in the area that we know now as Rome. So maybe to some extent the little red dots will also help us understand how the entire population of black holes formed.
Wasn't Rome founded by Romulus and Remus, who were raised by wolves?
Well, maybe they settled it actually very close to the thing. So it was actually a very important passage to go from one place to another because it was the only place in the Tiber that you could actually cross. So regarding the first black holes or the black hole seeds, as I was mentioning at the beginning, the real problem of the origin of the first black holes is really a problem of understanding if heavy seeding happened, because we know that light seeding happened. We know that there are supermassive black holes at very high redshift, and these black holes, they need to grow from smaller units, and they typically have a short time, alpha billion year approximately to grow. So they can even be formed as POP3 seeds, typically 100 solar masses, and they need to grow very fast to reach the supermassive black hole scale, or they are formed as heavy black hole seeds, typically 10 to the 4 to 10 to the 5 solar masses, through the direct collapse black hole scenario, or DCBH, for example. So how do we probe the seed population to understand how baby black holes can grow up? Typically there are two methods. One is to study the properties of the host galaxies, and two is a direct detection of heavy black hole seeds. Regarding the first method, there are several papers showing that if heavy seeding occurred in the High-Redshift universe, they are characterized by a very high black hole mass to stellar mass ratio at the beginning, and this ratio would decrease towards the local relation, so 1/1000, as time passes. There are many simulations showing this. For example, this is an evolutionary line for a direct collapse black hole, and you can see that it stays much higher, the local relation, which is this one, down to redshifts about 6 or 7. So it's very possible that with JWST we're actually witnessing just the fact that heavy seed stay over the local relation for a much longer time. Regarding the second method, so the direct detection, we know that the farthest black hole detected to date is about a redshift 10 or 11, while black hole seeds were formed around redshift 20 to 30. So by pushing the detection of black holes farther and farther out, we may be able to actually detect heavy seeds. So a few years ago, during my PhD, we actually made the first predictions for the spectrum emitted by a DCBH, and you can see that most of the light comes from the infrared and the X-ray. And based on these predictions, we made the first detailed calculations of the colors of DCBH, both in HST and with JWST. And now, last year, we actually came out with the first direct collapse black hole candidates that are also apparently detected in the X-ray. In the last couple of minutes, I just want to mention a possible connection to closer black holes, as promised. Before that, let me highlight this very recent, yes?
How do you know that was a direct collapse black hole?
So the photometry is very similar to what we find. It's also apparently detected in the X-rays. There are some skepticism about the X-ray detection because USC 111 is behind a cluster. So it's possible that it's just contamination, although it is a 4 sigma detection, but you know, the X-ray community is a little bit shaky about that. In this paper by Metzko and our collaborators, we found at redshift 1 to 3, so cosmic noon, some equivalents of very overmassive black holes that have black hole masses and stellar masses that are oddly similar to what we are detecting with JWST in the higher redshift regime. Different seeding scenarios in general will leave remnant signatures of seeding in local galaxies, especially dwarf galaxies. This plot in particular from Jenny Green shows different seeding scenarios, so mostly light seeds and heavy seeds. And you can see that we expect different tracks in the galaxy mass versus black hole mass relation in the local universe, especially in the low mass regime. And if they are formed from direct collapse, you expect them to be overmassive. I am a member of the AGN steering committee for the Habitable World Observatory, so HWO, and I proposed a science case to actually investigate different steering scenarios in local galaxies, in particular using the extraordinary angular resolution of HWO. We should be able to probe the spheral angular influence of black holes in local galaxies, even if they are quiescent. So we are not interested if they are accreting or not. So here, as a function of the distance, angular diameter distance, you see the minimum black hole mass that can be detected with HST, JWST, and two configurations of HWO. So basically, the goal is to discriminate whether supermassive black holes in local dwarf galaxies, and we calculated that we can probe about 15,000 of them. And we want to understand if they follow the local relation or they are very overmassive with respect to that. So this is my last slide, and during this talk we made quite a long journey across space and time, and to see just some examples of black hole populations that are not really well understood or completely undetected. So as a summary slide, I thought it would be nice to give a little visual representation of the populations that are still uncharted and charted. Here you can see basically what can be currently mappable with our most powerful X-ray and infrared telescopes. In particular, we can see very well supermassive black holes, intermediate mass black holes up to redshift 4 or 5, and stellar mass black holes really only in the local universe. So across the black hole horizon, there are certainly entire continents of black holes that are still yet to be discovered. Okay, thank you.
Any questions?
In the other scenario with extremely overdense stellar populations, how dense would that be? Is there likely to be collisions among stars, or is it still, spaced out enough to have no collisions?
So this is the point that I was trying to make. So we do think that at least in the extreme cases, so for 10 to the 8, 10 to the 9 solar masses per cubic parsec, you are in the regime in which you expect runaway stellar collisions. So the stars are, especially if they are pretty big stars, so if you have mass segregation of stars, so basically in a stellar cluster you have that the most massive stars are going towards the center, so they are preferentially the most massive stars close to the center, so they are bigger. It's very likely that at those densities they will just interact with each other and collide and form a very massive star. And you will form a black hole, and we're going to be happy with that.
So when these stars collide, how long does it take before they actually sort of become spherically symmetric and make a star again?
Oh, it's very fast. Once two stellar stars collide, I think there are some simulations 15 years ago in which they showed that it's much shorter than the dynamical time for the two stars. So
when you
yes.
say one star is much less mass, say if one star is much denser than the other, for example, it's not going to retain its integrity for a while before it dilutes?
I wouldn't think so. I'm not really an expert on this, on stellar collisions, like in actual simulations, but I would expect them to reach like a stable configuration after not such a long time. I remember that there were some simulations also for so direct collapse black holes are basically formed when you form like when you have the collapse of an entire gas cloud. So although it's not exactly the same condition, because in that case you would have a quasi-spherical gas collapsing, so not two things that are coming to each other. But in that case you have the collapse in a very short amount of time. So even if you are breaking the symmetry and you have two different stars, I don't expect the time to be much longer. The relativistic collapse would happen in a very short time.
And how about the angular momentum if you still have blobs, it's not perfectly spherically symmetric? Would you have too much angular momentum to form a black hole? Like,
So
the
it
Earth
helps.
would have too much angular momentum by far, right, to be a black hole?
Yeah, so you have to shed angular momentum, and it helps for sure that if there is gas around. In fact, in the analytical calculation that I showed, the mass added, you remember here, the mass added with here, the mass added to the very massive star is proportional to the star formation rate, because star formation rate also tracks gas that is at the center. So if there is gas, it's much simpler to shed angular momentum, yes. So in this scenario, at least if you have zero star formation rate, you have zero gas around, so you're not colliding stars. But in the n-body simulation that we are running, there is no gas there, and they are still colliding. So I don't think that, so gas would probably lead to more massive, very massive stars, but it's not the fundamental element to make the stars collide, especially if you're considering mass segregation of the
The
star.
colliding is, I understand, but I'm saying once you form this bigger star, which is not going to be instantly this nice and perfectly smooth, spherically symmetric object, right? It's going to have some residual inhomogeneities because of the former stars. And then this will collapse into a black hole without any problem? Even if you
I
have
mean,
some-
all the stars are spinning close to breakup at these times.
Right.
So there's no star that is a spherical. There's no spherical stars at redshift of 20 or whatever,
So
right?
I guess my point is, if you take the sun or any astrophysical object and you compute the spin over mass squared parameter, it's like way more than one. You know, this A over m parameter,
Why
that's
is
no
it
more than
really-
one,
You're
that's no
saying
more.
theoretically or
It's
observationally? or-
observation.
Just observational, yeah. Like the spin parameter for the black hole.
But it's even way bigger than that, because the
It's like
young
much
stars
larger.
are spinning close to breakup, so they're spinning enormously larger. Like they're not spherical objects, and
Right.
you know, a B star is not a spherical object, it's a pancake.
So like
So
the Earth
everything
has to
is-
be rotating super slowly to be allowed to form a black hole, right? Am I right? So I'm always wondering when people talk about this collapse.
I think it wouldn't be direct collapse, right? Won't it be that there'll be supernovae-like events? Like when two stars collide, don't they form this common envelope thing, which then leads to some early supernova type thing, which that is what creates the black hole, and then that thing accretes?
Yeah,
Or
that could be.
something?
The other thing is, as Fabio mentioned, there's stellar winds, which carry away a lot of angular momentum very efficiently, especially if they're magnetized. So,
But maybe once you have three stars in play, maybe more complicated things happen.
So kind of a lost con dynamics at that point. Yeah, I'm not really expert in stellar dynamics, so I'm not sure about that. We are not including the effect of angular momentum in, also because it's an n-body simulation, so they just collide.
There was a tremendous amount of very interesting information. Going back to the initial puzzle of the observation, I'm not sure I perceived that there was a bottom line in your view of these red dots and what they were, or were the dense stellar things, or did you come to a conclusion? And I just didn't quite.
So I can tell you my opinion.
Yeah.
I think most of them, some of them, if not most of them, all stage here.
Most of them are what?
Some of them, or most of them, they do all supermassive records. I don't see a world in which they are all stars. Even because if they are stars, the SCD is shaped in a way that would require an immense amount of star to fill up the absence of the central supermassive black hole. Okay, and the interesting question is here, I think. So assume that these things are only made of stars. Okay, so some of them are immensely dense in stars. So the question is, do we have to wait about 500 million years to see the formation of a possible black hole at the center, or are they already there? Meaning, did they form already in the past? Because if they are so dense now, they should be even denser before. But so we're seeing them now, so we're calculating the stellar density now. So is this happening, is this process of stellar collisions happening now, or is gonna happen in the next half a billion year? And in half a billion year, it's almost peak quasar activity. So if this is redshift 5 approximately, medium redshift, you wait half a billion year, 3/4 of a billion year, this is peak of quasar activity, basically, almost. So it's possible that we are forming, it's possible that this process could form supermassive black holes in some way, if they are really made up only of stars. But the punchline is that even if they are all made of stars right now, you can wait a bit and there is going to be a black hole there. So, yeah.
In the scenario where it is the extremely high density stars regions, what would be like a reasonable way for something like that to form when it's like so many orders of magnitude even denser than like the core of a globular cluster?
What would be the scenario? So
Yeah.
why would that fall? One possibility is that they are very low spin systems. So they are basically the low spin tail of the galaxy of the halo distribution function. And they are not rotating, so they are not extending, so they are just collapsing very close to the center. That's something that I thought about. So I don't see any other reason why you should compactify so many stars in such a small region, other than it's possibly wrong, meaning that there is actually a supermassive black hole at the center. But the funny thing is that there is no optimal solution here. So if you go to the stellar scenario, so let me go back to the beginning 1 second. If you go to the stellar scenario, you get extremely dense objects. If you go to the AGN dominated scenario, then you get black holes that are automatically overmassive. So there are not actually solutions in which you have a black hole that is close to the local relations. You can run any SCD modeling on these SCDs, assuming that there is a black hole. The black hole is always overmassive. There is no way these things are on the local relation. So in any case, these things are pretty wrong.
So have you seen any study where they tried to combine all these 3 different possibilities in one framework and they tried to see which one fits the observation better?
So people have been trying to do, also with the graduate student that I mentioned before, we've been trying to find compromises between these 2 extremes. So say that the AGN fraction is not 100%, it's just 50%, it's just 40%. So even assuming AGN fractions that are lower than 100%, still assuming that these are accreting around Eddington, the black hole mass is much more massive than it should be. So whenever you assume that there is a black hole there, for the particular shape of the SCD, it's a very peculiar V shape that people have not really seen. The bottom is at about 0.71 micron, something like that, so it's V shaped. So there is a bluer part that people typically think it's mostly from a young galaxy, and the redder part is mostly from the AGN, obscured maybe. But people are really struggling to reproduce this SCD with things that don't break the system, meaning that they are not completely overmassive or are not so massive as to being insanely dense. So people have been trying to find a compromise, but even if you go for a 50% AGN fraction, the black holes are still very overmassive.
But how do you combine this in the other hand where we know now, like also JWST discovered this very bright star formation? Like the too efficient star formation problem also in the early universe, right?
Yeah.
And if you have these massive black holes, then they might have stronger feedbacks that might shut down the star formation. So how would you reconcile both?
So this is so you're talking about JWST like universe breakers.
Yeah, I mean in the end, like also the same regime High-Redshift,
So some of these, for example, one of the first papers that pointed out the issue that you're talking about was the Lab in 2022, and the source is actually a good comparison with the little red dots because the effective radius is pretty small, but they found a stellar mass of 10 to the 10, 10 to the 11. So although they are not really little red dots because they are not as compact as these ones, also some of the galaxies that they are finding, assuming an SCD only made of stars, they are also extremely overmassive in stars. Yeah, it's very hard to understand what these things are because
It
it's
has to be one or another, right? It cannot be both, right? It cannot be like in the same galactic system, you have a very massive black hole and you still have a very high stellar mass.
Yeah, I mean, those are two extreme scenarios.
Right, so you can't have both.
Yes.
Having it
So-
half and half doesn't get you away from the extremists.
Yes.
So you only make your problem worse.
Some people, going back to your question, are actually suggesting that given that these things are extremely compact, so say that you have really in 100 parsec 10 to the 11 solar masses thing. If you do the calculation of the velocity dispersion of stars, only stars, you would get a velocity dispersion that is about 2,000, 3,000 kilometers per second. That is oddly similar to the how broad the lines are that we are observing. So the proposal was that only the velocity dispersion of stars could actually reproduce the breadth, how broad the H alpha line is. But on the other side, when you observe these lines, they indicate a density, like a gas, a neutron, an electron density at the core of these galaxies that is so high that people don't understand how it could be formed if not close to a supermassive black hole. So, I don't know. I'm sure there is a black hole there.
But it could be just like weak, very weak feedback. If you are in extremely weak feedback regime, then you might be able to form a very, you have a very high star formation at the same time. You have some
Feedback from the AGN, you mean?
Yeah, feedback from the
Yeah, it's possible. I agree.
Then you don't get the AGN helping you make the luminosity. I don't see the hybrid, it looks like it's even worse.
Okay.
But I'm very embarrassed not to be able to figure this out. But there's this, people talk a lot about a population of very high mass, high redshift black holes. And I thought that the masses of redshifts were sort of in the regime you're talking about.
Yeah.
But are your red dots the same as those others, or are these a separate
So you're
population?
talking about black hole seeds?
No, I'm talking about in this observed supposedly observed black holes at very high redshift and high mass, where by very high redshift, I only mean redshift of 7 or 8.
Yes, so these are the same sources that we're talking about. So quasars, the farthest quasar, so by quasar I mean an extremely luminous black hole. So typically on the 10 to the 8, 10 to the 10 solar masses, so more massive than those. The farthest one is a redshift 7.6 right now. The farthest black hole that was found is GNZ11, which hosts a black hole about 10.6.5 solar masses, so pretty small. And this is a redshift 10.6.
I somehow thought I heard not that long ago that there had been a mistake and it was actually at redshift 3 or something. Is that some other object? I mean, I made up the 3,
I'm not
maybe
sure
it was 5.
which one you're talking about exactly, but there have been some controversy about some galaxies, but GNZ11 is a redshift 10.6 actually. This is spectroscopically confirmed. There was some galaxy in which the second solution for the redshift was actually an interloper, a redshift 3 as you were saying, but wasn't GNZ11. GNZ11 is,
It's really robust.
yeah.
And
this
its
is a
mass is what?
10.6, 10 to the 6.5, so it's pretty small. But the GNZ11 is not a little red dot, it's a bigger system.
But then let's talk about, something at kind of the nice solar masses. What would be when people talk about the problem of very high redshift, but by high redshift I mean 7 or 8, not 10. I
Yes.
just want to know, is that the same as your red dots, or is there a different population?
So let's see. So these are typically quasars, okay? And the farthest quasar
Sorry, oh,
that was detected is a redshift 7.6, okay?
right, so your pointer is pointing to a redshift of 20.
I think it's a different from your screen and the screen.
Oh, that would explain some of the earlier times.
And now,
It was very
yeah,
confusing.
this was.
No,
What's
so
wrong with?
these are quasars, and these are the farthest redshift quasar. These are 7.6, okay? Here. And this is a redshift 10 to the 9 solar mass. I think I have a...
Is there a pointer?
Yeah, actually, I have it,
That's showing even more up there around 8. But so the blue, I see, so that your red dots are the ones that are shown as blue dots, is that right?
Yes, correct. Yeah, I could change that.
And yeah, you really should. And that they're characterized by being visibly, measurably extended, and you could sometimes measure them. Is that a way to think about it?
Visually extended the
I
little
mean,
dots. What do you
Tell
mean?
me the difference between your red dots and the quasars further to the right.
Oh,
The
in
little black dots.
so observationally, the difference is in luminosity. Okay, the black holes, if there are black holes in the little red dots, they are 10 to the 45 to 10 to the 47 erg per second. If quasars are typically more luminous than 10 to the 47 erg per second, so that's an observational difference. Quasars are brighter and typically are associated with bigger masses. Quasars, typically we talk about black
So the
holes.
ones that people have been speaking about as being anomalous are the ones that, from your terminology, quasars.
For the formation, yes, absolutely, because
But also in terms of just what, in your plot, they're quasars.
yes, because the problem of the quasars is that they are very big, very soon in the history of the universe. So if you form a 10 to the 10 solar mass as a redshift 7, it's very hard. There is no problem in forming the little red dots, even from light seeds. This is what I was trying to convey with this plot.
I was
Yeah,
not
because
sure whether you were talking about one and the same.
yes, no, quasars are more massive, and those are the ones that are problematic to form in mass. The little red dots, if they do contain black holes, these black holes are not very massive. Actually, they can even be formed from light seeds. We don't need heavy seeds. The problem is that they are overmassive with respect to the galaxy. So they are not very massive by themselves. They are pretty small, actually. They are just too massive for the galaxy that they are contained in.
Maybe the galaxy is too small.
Yes.
Different point of view.
Yes, so small.
But they measure their mass through lensing, right? We know the mass of the guys are more or less correct.
So the masses of the black holes are estimated via H alpha.
And the galaxies?
The galaxy size is actually measured in filters. So you can, if you know the PSF of JWST, you can actually compute a given, say 7 pixels, as I was saying before, what's the physical size of 7 pixels.
But the whole chunk's mass, we know it, right? More or less.
The
whole chunks, like the halo and the galaxy, everything, we know the mass of it now.
I mean, you can estimate the mass of the yellow from the stars, but you don't measure it.
I think maybe we should just thank
Yeah, yeah,
Fabio.
yeah.
And,
Thank you very much.
Yeah, I'm happy to chat more whenever you want.
Calculate that.
Are you leaving today or you staying?
Tomorrow,
So you're coming here tomorrow?
yes, in the morning.